methane, ammonia, water, hydrogen fluoride and ethanol. You should already know what covalent bonds are and how they form. If you need to refresh, you might want to watch our video, Covalent Bonds, before you continue. So what are methane, ammonia, water and hydrogen fluoride, and why are they special? All of these compounds are small, covalently bonded molecules. The atoms within them share electrons because they have half-full or more than half-full valence shells of electrons. That is, they are non-metals. Methane is a fuel, ammonia is used in household cleaners, water is a drink and the essence of life, and hydrogen fluoride is used to etch glass. The bonding in methane, ammonia, water and hydrogen fluoride shows a pattern. Methane is carbon, bonded to 4 hydrogen atoms. Ammonia is nitrogen, bonded to 3 hydrogen atoms. Water is oxygen, bonded to, guess how many? 2 hydrogen atoms. And hydrogen fluoride is fluorine, bonded to just 1 hydrogen atom. Carbon, nitrogen, oxygen and fluorine appear in the periodic table in this order, moving along the second row from left to right. Carbon has 4 out of 8 electrons in its outer shell, so makes 4 covalent bonds. Nitrogen has 5 out of 8 electrons in its outer shell, so can make 3 covalent bonds to make the shell full. Oxygen has 6 electrons in its outer shell. It can bond with 2 hydrogen atoms to share 2 more electrons. It now has a full outer shell of 8 electrons. We can draw the covalent bonding in these molecules using dot and cross diagrams. You should already have watched our video on dot and cross diagrams. Methane, ammonia and water bond like this. You can also represent them using rings to show the orbitals. Can you draw a dot and cross diagram for hydrogen fluoride? Pause the video and have a go. Have you got it? Each structure contains 4 pairs of electrons that sit as far apart as possible. In methane, all 4 are in bonds. This makes methane tetrahedral in shape. Look at what happens when we draw methane, ammonia, water and hydrogen fluoride. Let's look at these shapes more closely. Ammonia has 2 electrons, called a lone pair of electrons, occupying the 4th position. These electrons take up space. We can't pretend they're not there. In fact, because electrons are negatively charged, lone pairs repel bonds even more strongly than bonds repel each other. This makes ammonia less symmetric than methane. The water molecule is bent in shape. Oxygen has 2 lone pairs. Negatively charged lone pairs are slightly attracted to the hydrogen atoms, so there is a weak attraction between molecules. Forces between molecules are a little stronger in water than in ammonia or methane. Water is liquid at room temperature and pressure, whilst ammonia is a gas that is easily liquefied, and methane is a gas. Intermolecular forces are normally very weak in covalent compounds, but in water they are just strong enough to keep it a liquid. A bit more energy is needed to overcome these forces and boil it. If water were not a liquid, life as we know it would be completely different. Now let's look at something a little harder. Ethanol. This contains carbon and oxygen bonding. How would you draw the 2 kinds of dot and cross diagrams of ethanol? Pause the video whilst you figure it out. Ready for the answer? Dot and cross diagrams of ethanol would look like this. Don't worry if you drew the dots or crosses the other way around, that is also correct. As you can see, the carbon atoms always form 4 bonds, and the oxygen forms 2. We can also draw this molecule using lines to represent bonds. This is the displayed formula. Here they are again. You can see the displayed formula of 2 kinds of dot and cross diagram. By now, you should be comfortable with covalent bonding, and familiar with these structures and the ways they arrange themselves in space. Remember, carbon forms 4 bonds, nitrogen forms 3 bonds, and has 1 lone pair of electrons, and oxygen forms 2 bonds and looks bent. You should remember that lone pairs of electrons take up space and repel more than bonds do, and note the pattern in these structures as you travel along the row of the periodic table.